This is the Automotive Repair Podcast Network.
Welcome, everyone, to yet another episode of Diagnosing the Aftermarket A to Z. I'm Matt Fonslow, and bubbles everywhere and not a drop to drink. That and more after a word from our sponsor, Pico Technology. Tired of guesswork in your auto diagnostics? Need to pinpoint faults quickly and accurately? PicoScope will turn your PC into a powerful diagnostic tool. See live waveforms from sensors, injectors, and ignition systems. See the problem? Solve it faster. Visit picoauto.com. That's Pico auto.com. I got on a binge watching The Science of Bubbles, and I'm not talking about the ape. There's a lot of power in bubbles, surprisingly so. And I guess it shouldn't be a surprise. I don't have a boat. I've never owned a boat. My family's never owned a boat, but I know what happens to props. Also, working in this profession, we see what happens to particularly water pumps. I think coming out of college, I thought most of the damage was due to like electrolysis. And there is that, but it really turns out damage is done by cavitation. So I'm watching this documentary on bubbles, and it starts to occur to me, this translates directly into our world. I don't know that many of us approach cooling system maintenance from a anti-cavitation point of view. I don't think we think about it. Short of we don't want it. We know it's bad. But why does it happen? These little bubbles, so what? But it turns out, I mean, it's not a lot to it, but there is. It's amazing. For one, it's not so much the bubble itself forming, it's the collapse. And the amount of energy released in that collapse is really impressive. You got to be careful how this is conveyed, because it's true, but it doesn't necessarily mean you can't really go running with this, or you shouldn't go running with this. But temperatures generated by a collapsing bubble can rival that of the surface of the sun, depending on where we consider the surface and all that. But it's hot. The thing is, it doesn't really necessarily transfer to anything because you have this small amount of that temperature surrounded by quite a volume of much lower temperature water or coolant. That's just the beginning of it. Where the real damage starts occurring is when they collapse, they kind of form really what looks like a donut. And through that center of that donut, perpendicular to the ring, if you will, in one direction is a very, very powerful and narrow in diameter microjet stream. When this is released nearby really anything solid, it starts to do damage. It starts to form that pitting that we associate with cavitation. I mean, I find that amazing. And then on top of that, and don't get me wrong, the majority of the damage is from that microjet. Another phenomenon is the kind of a shock wave, a sound shock wave, not unlike really a jet or a whip, the tip of a whip breaking the sound barrier. You get that crack from the whip. That's the sound barrier being broken and the air rushing back to fill in that space and kind of slapping together. That happens with the water at very small scales, but it still happens. It still emits. And when it's near something, I want to say it affects the surface. I don't want to say immediately it does damage. This is why ultrasonic cleaning works, partially at least. I find that fascinating. The moral of the story is we want to stop that. So thank you for listening. How do the bubbles form? Really, like if we have this cooling system filled, how in the world do these bubbles form? And I guess I would first ask, what happens to water if you boil it near sea level? Like where I live, we're pretty close to sea level. I think maybe about 500 feet above, roughly. It takes pretty darn close to 100 degrees Celsius or 212 degrees Fahrenheit. What about everybody in Denver? How high does the temperature have to be there? We don't need to know the answer. We just know it's less. When we're evacuating an AC system, now granted, we have, refrigerant in there, but we're trying to get the moisture out if there is any. We put it under a pretty deep vacuum. Why? Because it greatly reduces the temperature for boiling. It allows water to literally boil at ambient air temp well below 100 degrees Celsius. So we know that pressure is very important to this, right? The boiling, you're just watching a pot of water boil, you're seeing bubbles, right? Steam bubbles. And that's primarily what's inside these bubbles is steam, vaporized water. It's allowed to boil when, I guess we would call it local pressure, is not high enough to prevent the vapor pressure from forming. And so it's exceeded by that vapor pressure, and then we start forming bubbles. And there's mainly steam. Yeah, in some cases, there's like nitrogen and just other atmospheric gases and maybe very, very minor levels of like water separating, but it's really non-factor. It's mainly the steam, the vapor. Well, okay, we have the system under pressure. So why is this a thing? Well, it's very important that we do have pressure on the system. That is one of the reasons why also we want to, of course, raise that boiling point so we can have our coolant temperatures go above that, not boil over, certain emissions, reasons, stuff like that. But also to prevent cavitation, maybe almost primarily. And still, it could happen. And the reason is, if you think about what's going on in the cooling system, we have a pump, and that pump spins inside or surrounded by the coolant. Just think about it as a old style fan with the big propellers on it, if you will, or impeller. It's probably a technical term, right? The blades. One side is going to be pressure, but the other side is creating a low pressure area. How low? And what happens to affect that? Now, granted, we have water pump designs and that's a heavy factor, but other things can start to play a role in what's going to allow lower pressure, if you will. And that can be contamination. We start getting kind of a convergence of factors that start overlapping. We have multiple reasons to want certain things, but not to jump around. I guess I'll just stick with it. It's that low pressure caused by the impellers spinning inside of the liquid that starts to form bubbles. The pressure drops behind, on that opposite end, on that feed side, if you will, just for plain talk. That's one place. Another place is just along the surfaces of the interior of wherever the coolant passages are, wherever you can get a speed change. So that could be any sort of restrictions. And I guess restrictions where we might have a diameter change by design, or maybe arguably a bad design. Also by contamination, like something has formed, deposits have formed and then created a spot where we get a pressure drop. And if the pressure drops enough, if that pressure goes low enough, that local pressure, we can get bubbles forming. And it turns out the bubbles will form on that kind of that backside of that pump, as well as along the surfaces. And that's why we can get pitting in other places like heater cores, radiators. And those microjets are going to affect the softer metals long before they're going to affect the harder metals, right? I mean, that just makes perfect sense. It's just kind of fascinating stuff to me. I guess maybe I need a life, but I guess it means something to think about it in these terms, because now I find myself approaching cooling system maintenance from a different perspective. How do I keep this cavitation from occurring? Number one, the radiator cap or the cooling system cap, which we really need to stop calling such a thing, or at least amongst ourselves, take a page out of somebody that actually works for this Sponsor of the podcast, Pico Technology, specifically Pico USA, Randy Dillman, in a class. Wow. This is going to be Cicera 2007, maybe. CAN conference in Chicago. Does a presentation on cooling systems. A better term for the cooling system cap or the radiator cap is the degassing cap. Its job is to keep the proper amount of pressure in the system, right? They're rated. We need to be testing these things regularly. Should be 15 PSI. It should be 16 PSI. That is really, really important that it maintains that pressure because it's going to keep the local pressure high enough above that vapor pressure threshold. And honestly, I think there's a technical term, net positive suction head available. That's the technical term. That its job is to keep that pressure up higher and then, as high as it can. It's also to burp, right? Burp out that vapor, burp out air so that we have as pure a liquid as we can, or fluid. Got to be careful when we start using terms like that. So liquid, we have to say liquid because fluid, honestly, air is a fluid. We got to keep the liquid as possible. 100%, quote unquote, 100%. Is your shop ready for the electric vehicle revolution? Don't get left behind. The Picoscope EV Kit is your all-in-one solution. Diagnose any electric or hybrid vehicle, from high-voltage batteries to complex communication systems. With guided tests and pinpoint accuracy, you'll tackle more jobs and boost your bottom line. This isn't just a tool. It's your future. Be the expert in EV repair. Visit picoauto.com to future-proof your shop today. That's PICOauto.com. We should be referring to the cap as the degassing cap. And then after that, turns out, I guess I was kind of curious, like the coolant concentration matters as well as the inhibitor package. But I was wondering, like, how does that work? Like, what do they do? Like, what would be the chemical to prevent cavitation? And it turns out it doesn't necessarily prevent it. The idea is that the contents of that inhibitor package forms kind of a protective barrier on the surfaces. And that barrier absorbs the effects or the attack, if you will, of the microjet from the bubbles bursting. That wears out over time. So we can test coolant concentration percent, and we can test like the freeze point. But what do we have as a good test for the inhibitor package? We can test the pH. That might be a pretty decent indicator because if the inhibitor package for the pH level to keep that neutral or maybe slightly base, I don't know if anyone's actually technically slightly acidic off the cuff, but it would be somewhere in and around 7, right? Pretty close. That might be a fairly decent indicator. The other thing is just time. They recommend replacing it in certain time intervals, and then we observe those times. We test for what we can test, and if those fail, then we recommend based off those tests. So evidence-based. And then after that, time and mileage. And that's because that's what we have to go on, is if that package is kind of wore out, if you will, it no longer forms that protective barrier inside the cooling system. And that's why we can get cavitation. There maybe was some cavitation occurring, but we had that protective barrier protecting things. It didn't affect it, or it didn't affect it much. And as it wore out, it doesn't have it anymore. So now the damage occurs. The other thing is to use the proper water. The thing is we really don't want impurities. So using tap water might not be such a great idea, especially if you have a relatively high mineral content. The impurities kind of affect it in two different ways. One is you can get calcification, or you can get a buildup of this mineral deposit somewhere in the cooling system, creating what? A restriction that then creates low pressure areas that then create bubbles. Kind of interesting. And then just the fact of the floating debris, if you will, and debris wouldn't be nearly as big enough to be called debris, I suppose. But the fact that we have contamination in there that's not water, that's some impurity, like we'll just say a mineral, that itself can help create the bubble. It's just amazing. We should be looking at distilled water, or maybe reverse osmosis, or buying, where we can use the premixed that has the proper water in it and using the proper coolant. There isn't a universal coolant. These are now factors that, it's like I knew they were important, but I didn't understand why. And I feel like I have a better handle on it. This just popped in my head. I seem to remember reading about, and it was more back in the day, like old days, before my time, probably before most of our times, but at night on ships that had the big impellers or the big propellers, at night, a lot of the crew members, or depending on the nature of the ship, passengers would gather at the back and look down at the water where the propeller was, because you could see flickers of light, flashes of light from those bubbles bursting, indicative of the temperatures that we're seeing hit when those bubbles burst. That's an insane amount of energy, so small, but over time it erodes, right? It cavitates, it pits. The name, I think the phenomenon is like sonoluminescence. I think I'm almost positive that's what it's called. Should probably look it up, but yeah, sonoluminescence. Sono would be sound, right? The collapsing, creating that ultrasonic wave or sound wave, if you will. It's craziness. But I feel like now, armed with this information, not only would I have my mechanical and technical specialists approaching vehicles a little differently, at least the cooling systems and the cooling system maintenance and the recommendations, but now also explaining to customers why this is important. Honestly, off the cuff, I've never heard a shop service advisor. I've never read about one stating to a client or discussing a story of interacting with a client where they've talked about restoring that protective barrier in the coolant passages of your cooling system. And you can say that, and you're absolutely correct. That's good stuff, right? I guess this is stuff that really drives me. But just finding out about this stuff, I hope you find it as interesting as I do. And that, you start approaching clients and just the vehicles, a little different perspective, a little bit different thought process, and start adding more testing to your regular maintenance intervals or maintenance services for the cooling system, where you are testing for pH, concentration, probably using a hygrorefractometer. I don't know if the floating balls are going to hack it. And then one more test is using your voltmeter, testing for voltage potential. It might be cooling system related. You have to do your due diligence if you have a reading, to verify actual grounds circuit. But then also it might be another indicator that the additive package, the inhibitor package with that coolant is used up. That is how I'll leave you. I really, really appreciate listening. I hope you got something out of this. I hope it kind of arms you and maybe can reinvigorate everyone on how to handle cooling system maintenance and to start becoming a little more proactive where it comes to water quality, using the right coolants, the real deals, not the universals. And of course, the degassing cap. Thank you to our sponsor, Pico Technology. Thank you, Randy, for that class you did at Cannes so long ago that I think I know where the book is now that I think about it. But fascinating subject. Thank you to the Automotive Repair Podcast Network for letting me do this. And until next time, take care.
You've been listening to Diagnosing the Aftermarket A to Z with Matt Fonslow on the Automotive Repair Podcast Network. Download our exclusive podcast app at automotiverepairpodcastnetwork.com, because the best conversations in the industry start here. Want Matt to cover a specific topic? Check the show notes for his email. Your input matters.